In 1998, two teams of astronomers stared at data from over 50 distant exploding stars. They were trying to measure exactly how much the universe's expansion was slowing down. Instead, the numbers showed something impossible. The universe wasn't slowing down at all. It was hitting the gas pedal, flying apart faster every single second. That single observation revealed a massive, invisible engine driving the cosmos and exposed a staggering truth. Everything we can see, touch, and interact with makes up just 5% of reality. Look around you. The screen you are watching this on, the chair you are sitting in, the earth beneath your feet, and every single star in the night sky. All of it, every atom of ordinary matter, accounts for 4.9% of the universe. So what is the other 95%? Cosmologists divide the missing universe into two massive categories: dark matter, which makes up about 27%, and dark energy, which dominates at roughly 68%. But here's the thing. The only thing these two forces actually have in common is the word dark. And in physics, dark is just a placeholder word for "we have no idea what this is yet." They are in fact complete opposites. Dark matter pulls things together through gravity. It acts as an invisible scaffolding that holds galaxies and galaxy clusters intact. Dark energy pushes things apart. It's gravitationally repulsive, spreading uniformly throughout space and driving the universe's accelerated expansion. One builds the cosmic web, the other stretches it until it breaks. The story of dark matter starts in 1933 with a Swiss astronomer named Fritz Zwicky. He was studying the Coma galaxy cluster, measuring how fast the galaxies were moving. When he applied the virial theorem to estimate the cluster's mass based on those speeds, the math broke. The galaxies were moving so fast that they should have been flung out into deep space. To keep them bound together, the cluster needed to contain 10 times more mass than what was visible. Zwicky coined the term dunkle materia, or dark matter. And for decades, the scientific community mostly ignored him. That changed in the 1970s. Astronomer Vera Rubin, using a highly sensitive new spectrograph developed by her collaborator Kent Ford, started measuring how fast stars orbit their galactic centers. Basic physics tells us that stars on the outer edges of a galaxy should orbit slower than those near the dense core, much like Neptune orbits the Sun far slower than Mercury. But Rubin found something astonishing. The stars on the outskirts were moving just as fast as the ones near the center. The result was a flat rotation curve. The only physical way this is possible is if galaxies contain 5 to 10 times more mass than we can see, extending far beyond the visible stars. If there was any lingering doubt, it was crushed in 2006 by the Bullet Cluster. Two massive galaxy clusters collided at 4,500 kilometers per second, one of the most energetic events since the beginning of the cosmos. When astronomers looked at the collision, they saw the hot gas of ordinary matter crash and slow down, creating a massive bow shock. But gravitational lensing, the bending of background light around massive objects, revealed that the vast majority of the mass just kept going, passing right through the collision without slowing down at all. It was direct visual evidence. Dark matter does not interact with light or electromagnetism. It only interacts with gravity. How do you detect a particle that passes right through solid matter as if it is not even there? You build a trap and you wait. For decades, the leading candidates for dark matter have been WIMPs, weakly interacting massive particles. To catch one, scientists built the LUX-ZEPLIN, or LZ experiment. They went 4,850 feet underground into a facility in Lead, South Dakota, to block out background cosmic rays. Down there, They built a two-phase time projection chamber and filled it with 7,000 kilograms of liquid xenon cooled to -160 degrees Fahrenheit. The idea is simple, but incredibly difficult to execute. If a WIMP passes through Earth and happens to strike a xenon nucleus, it will create a tiny low-energy recoil. The detector looks for a very specific signature, a primary flash of scintillation light, followed by a secondary flash from drifting electrons. If the first flash is brighter than the second, you might have just caught dark matter. But so far, nothing. This has led physicists to look at other candidates, like axions. Axions are hypothetical particles much lighter than WIMPs. Instead of giant vats of liquid xenon, detecting axions require powerful magnets chilled to nearly absolute zero, attempting to force the invisible axion to transform into a detectable photon. And recently, the James Webb Space Telescope has thrown entirely new data into the mix. In late 2025, JWST observations suggested that the very first stars in the universe might not have been powered by nuclear fusion at all. Instead, they might have been supermassive dark stars powered by the heat of dark matter particles annihilating each other in their dense cores. While dark matter holds galaxies together, dark energy is tearing the universe apart. When those two teams of astronomers in 1998 looked at Type 1a supernovae, exploding white dwarfs that act as standard cosmic candles, they realized the light was 10 to 15% dimmer than expected. The supernovae were farther away than the math predicted. The expansion of the universe was accelerating. The simplest explanation for dark energy is the cosmological constant, represented by the Greek letter lambda. It is the intrinsic, fundamental energy of empty space itself. As the universe expands, ordinary matter dilutes and spreads out, but dark energy does not. A cubic meter of empty space always has the exact same amount of dark energy. But this creates what is arguably one of the deepest unresolved problems in theoretical physics. When quantum field theorists calculate how much vacuum energy should exist in empty space, the number they get is 50 to 120 orders of magnitude larger than what we actually observe. It is a discrepancy so massive, it tells us our fundamental understanding of physics is missing a massive puzzle piece. To figure out what dark energy actually is, we need to measure the universe with extreme precision. And to do that, cosmologists use something called baryon acoustic oscillations, or BAO. Think of BAO as a cosmic standard ruler. In the primordial plasma of the early cosmos, the battle between gravity pulling matter inward and radiation pushing it outward created massive acoustic density waves, literal sound waves rippling through the cosmos. About 380,000 years after the beginning of the cosmos, the universe cooled, and those waves froze in place. Today, the distance between those frozen ripples has stretched to about 490 million light-years. By measuring the distance between galaxies today, we can use that 490 million light-year ruler to track exactly how fast the universe expanded at different points in time. In March 2025, the Dark Energy Spectroscopic Instrument, or DESI, released a monumental breakthrough. Using a massive fiber spectrograph, they mapped 18.7 million objects, creating the most detailed three-dimensional map of the universe ever made. And the data revealed a shock. For decades, we assumed dark energy was a constant, unchanging force, but the DESI data suggests dark energy might actually be dynamic. Its influence appears to be weakening over cosmic time. Right now, the statistical significance sits between 2.8 and 4.2 sigma. In physics, you need a 5 sigma result to claim an official discovery, so we need more data, but the hints are incredibly strong. The engine driving the universe apart might be shifting gears. We have mapped the cosmos, peered back to the dawn of time, and measured the expansion of space itself. But everything we understand, every star, planet, and person, is just a 5% rounding error in a universe dominated by invisible forces. We are made of the rarest ingredients in the cosmos. So, I want to hear your thoughts. If the 2025 DESI data is right and dark energy is actually weakening over time, what do you think that means for the ultimate fate of our universe? Let me know down in the comments. And if you want to help this channel fight back against the expanding void, you don't need dark matter to pull things together. Just hit that like button and subscribe to LynxSifts. It acts as the perfect gravitational anchor for more science and technology deep dives. Thanks for watching, and I will see you in the next one.